All right, so we're going to be continuing on with our titration calculations. We are going to be focusing on starting with a weak acid and adding a strong base to it. Now, this is the slide that we left off on the previous presentation, but it's really worth going back and talking about it. So we're going to calculate the pH at these 4 different spots. With no base added, this would just be our initial pH, and we know how to do that. So we have the Ka of the acid, we have the concentration of the acid, we do an ice chart, we solve for H+, and then find pH. So that we know how to do. Then our next point is half equivalence point, and I'll go through this calculation in 2 different ways. One, doing the shortcut, where pH equals pKa at half equivalence point, and 2, plugging it into Ka as a common ion calculation, because sometimes you might not realize you're at half equivalence point and you do the whole thing. But if you realize you're at half equivalence point, it will save you so much time. And again, we would know that we're at half equivalence point by doing MAVA. So we are adding 0.1 molar sodium hydroxide. We have 0.1 molar acetic acid and 50 milliliters of it. So doing MAVA, math is super easy here. We would recognize that we would be at equivalence point at 50 milliliters. So therefore, we would be at half equivalence point at 25 milliliters. Okay, so then when we get to equivalence point, then the way that we calculate our pH is by acknowledging that all of our acid's been consumed, all of the base has been consumed, but we have made the acetate ion, which is the conjugate base of a weak acid, therefore our solution will be acidic. So, or basic, sorry. So we will have to do a Kb calculation, find the OH concentration. From OH we find POH, and therefore we will find pH. Then our last part, easy, we have some excess sodium hydroxide. So from the excess OH, you can find POH and then find pH. So we're going to go through each one of those parts individually. All right, so our first part is just the initial pH. So it's always helpful to write our equation. So we have our weak acid. We can just do the HA shortcut, or we can write out the whole formula for acetic acid. Either way is perfectly fine. I'm just going to do the shortcut, make it a little bit easier. All right, so we know we're starting with 0.1 molar. We would have none and none. We're going to lose X, gain X, gain X. So therefore, at equilibrium, we will have 0.1 minus X, X, and X. Now we can do our assumption that because Ka is small, and we would need to acknowledge this on a test, a quiz, or the AP exam, because Ka is small, X will be small too, or even very small. Therefore, 0.1 minus X is approximately equal to 0.1. All right, then once we have that out of the way, we can plug everything into our Ka expression. And we always want to write our full Ka expression. So it would be Ka is equal to H plus times A minus over HA. All right, and we know our Ka value. They would have to give that to you. Acetic acid is 1.8 times 10 to the negative fifth, so that would have to be given in the problem or solved for previously in the problem. That's going to be equal to x squared over 0.1. So then we grab our calculators and do our math. We get x squared is equal to 1.8 times 10 to the negative 6. So then we take the square root of that, And we get X having a value of 1.34 times 10 to the negative third, and that would be molarity, and that's equal to H plus. Therefore, in order to find the pH, it would be the negative log of that concentration that we just found. That should be a negative in there. So we plug that into our calculator and get 2.87. We do need to check significant figures. We are starting with 3, so therefore we will need 3 digits after the decimal. So my pH is going to be 2.872. And that does sound reasonable for a weak acid, so we know we are in the right range. The next part of our calculation is finding the pH at half equivalence point. So again, equivalence point was at 50 milliliters for this problem. So at 25 milliliters, then it's going to be half equivalence point. So we can use this super valuable shortcut. If you're considering getting any chemistry tattoos, pH equals pKa at half equivalence point would be a great one to get, along with if delta G is negative, our reaction is thermodynamically favored. All right, so we just acknowledge that we are at half equivalence point. Therefore, pH equals pKa. So pH is equal to the negative log of 1.8 times 10 to the negative fifth. And that would give us 4.74. And I just realized a mistake I made on the previous slide. Since we were working with this, we only had 2 significant figures, so that previous answer that I did should have only had 2 digits after the decimal for the pH. Sorry about that. Okay, so that part's very easy. I am going to backtrack a little bit and talk about what would have happened if we had forgotten this shortcut, because I do want to show you that we can still figure it out if we had forgotten the shortcut. Okay, so we would have started with writing out our equation. So we have the acetic acid plus the NaOH makes water and a salt. Now I'm still using the generic A for the anion instead of the acetate, and that's just so my writing's easier, but you definitely could have done acetic acid over here, and then this would be sodium acetate. Okay, so we can figure out the moles of acetic acid that we had originally. So present, we had 0.1 molar acetic acid. You know what, I'm going to move this down here a little bit because I'm going to need to write over there in a little while. Okay, so we have 0.1 molars of acetic acid, and we had 50 milliliters, so 50 milliliters would be 0.5 liters. So therefore, we have 0.005 moles of the acetic acid present initially. And again, I really like to label as much as I possibly can. All right, we have added 25 milliliters of NaOH. So we had 0.1 molar NaOH. 25 milliliters would be 0.25 liters. Therefore, when we multiply those together, we would get 0.0025 moles of base. Okay, so then we think about our stoichiometry. If we have 0.005 of that present, moles, and 0.025 moles of sodium hydroxide present. They're in a 1-to-1 ratio. Therefore, sodium hydroxide is our limiting reactant. So we would lose 0.025. So we have no sodium hydroxide. We would have 0.025 moles of acid remaining because we started with 0.05. 0.025 have been consumed, so 0.025 remains. We're going to produce some water. We don't really care about that. And we're going to produce our salt. Since 0.025 was my limiting reactant, they're in a 1-to-1 ratio, I would produce 0.025 moles of my salt. So when I go to do my Ka calculation, I do have to take into account the molarity of my acid and the molarity of my conjugate base. And again, I don't really care about the sodium ion in there. I care about the A- there. Because if we think about our acid equation, HA dissociates into H plus and A-. And this is where people start to get confused because we have two equations happening. So this is our neutralization, but we are definitely still in the acidic range. So therefore we have to also deal with the acid equilibrium. So then we're going to be doing a K calculation. So Ka is equal to the concentration of H plus times the concentration of A- over the concentration of HA. We have their moles. We need to figure out their molarities. So we have to take these moles here that we got here, and we've got to convert them back to molarity. And we need to make sure that we take into account the new diluted volume. So I'm going to erase some of this stuff here just so that I got some space to work. All right, so in order to get my HA, we need way smaller. Okay. Okay. So in order to figure out the concentration of the acetic acid that is present at this point, I would take my moles of acetic acid that remain, 0.025, and divide by my new total volume. My new total volume, I had 50 milliliters of the acid, 25 milliliters of the base have been added. So my new total volume is 75 milliliters or 0.75 liters. So I divide those out. And that gives me the concentration of my acid at this moment in the titration. So that will be going into my Ka calculation. I gotta do the same thing for the A-. So I happen to have 0.025 moles, and I also happen to have 0.75 liters because obviously they're all in the container together, so they're all going to have the same volume. So that is also going to be 0.33. Okay. Now I know my Ka calculation. Since I am running out of space, I do need to erase some of that. This is where having the two boards in my classroom is super, super, super helpful. Okay, so I know my Ka is 1.8 times 10 to the negative fifth. I'm solving for the H plus concentration. I know my A minus is 0.033. I know my HA is 0.033. So I do my math, those terms drop out. I get X is equal to 1.8 times 10 to the negative fifth. In order to find the pH, I do negative log of 1.8 times 10 to the negative fifth, which now you recognize is pH equals the negative log of the Ka. So my whole point here is to show you that if we used that shortcut of pH equals pKa at half equivalence point, we would have saved ourselves a considerable amount of time. But we can still get there even if we forgot to recognize that we had that shortcut. All right, at equivalence point can be a little bit time consuming, but honestly, as long as you just work through slowly, take your time, label everything, it's not bad. So you have to think about what's happening at equivalence point. So all of the acetic acid has reacted. There's no excess sodium hydroxide. That has all reacted too. We've made water and a salt. Our salt is going to be sodium acetate in this case. The acetate ion is a weak base, so therefore we're going to have a pH a little bit above 7. And the thing that's going to be important here is how much acetate we have. If we know how much acetate we have, then we can do a Kb calculation because it's acting as a base, so we need to do Kb. And then we can find OH, POH, and pH. This again just summarizes what we're going to need to do. We're going to need to find the moles of acid that had been present, and we actually did that earlier. The moles of base that are present, then we'll see that those are both consumed, see how many moles of conjugate base we produced, turn it into molarity. Then we also will have to solve for Kb using Ka times Kb equals Kw, then find our OH concentration, then find POH and pH. So it really nicely uses all of the skills that we've been working with. All right, so moles of acid, we actually already found this earlier, but we can re-find it. We had 0.1 molar acetic acid, and we originally had 50 milliliters of that. So therefore, we would have 0.5 liters. So then we would have 0.005, or 5 times 10 to the negative third, moles of the weak acid present initially. Okay, we also have the exact same amount of base has been added because 0.1 and we added 50 milliliters. Okay, then we think about the reaction that we've been doing. This is an acid-base neutralization. So our weak acid plus our strong base makes water and a salt. Again, for simplicity's sake, I'm using A minus instead of the acetate ion because I don't have a huge amount of space to work with. All right, so back to stoichiometry. If I have 0.005 moles of my weak acid and 0.005 moles of sodium hydroxide, they will totally react. They are technically both the limiting reactant. They'll make some water. We don't really care about that. And they will produce 0.005 moles of our salt will be produced. Because these will totally react, go down to 0, totally react, go down to 0, but they will produce that much of our conjugate base. And again, we don't care about the sodium ion. That's not going to affect our pH, but the conjugate base will certainly affect our pH. All right, now we need that to be in molarity. So while our moles are helpful to go into any of our K expressions, it's got to be concentration. So we will take the 0.005 moles of the A minus that we produced and divide by our total volume. Now our total volume is 100 milliliters because I had 50 milliliters of acid originally and I added 50 milliliters of base. So it's 0.1. So 0.005 divided by 0.1 would just be 0.5. Now I'm ready to plug everything into my KB expression. And I need to actually find KB and I need to write my equation. So first we'll do the easier part, finding KB. So Ka times Kb equals Kw. So Kb is going to be 1 times 10 to the negative 14. That's Ka, or Kw, divided by acetic acid's Ka, which is 1.8 times 10 to the negative 5th. And that gives us 5.6 times 10 to the negative 10th, I believe that is. Let me just check that real quick. Yep, 5.6 times 10 to the negative 10th. All right, I also need to write my equation that I'm going to be doing. So writing your equations can be kind of tricky. You got to think about the major thing that's affecting the pH. Right now, my major thing affecting the pH is the conjugate base. So that plus water, because we definitely have water present, will make HA times OH minus, because the conjugate base would gain an H plus, water would lose an H plus. Therefore, my KB expression would be HA times OH minus over the A minus concentration. My KB value is 5.6 times 10 to the negative 10th. My HA and OH minus would be X squared. A minus would be 0.05. And then I do my math. And I get for my OH concentration, okay, so we do our math here. 5.6 times 10 to the negative 10th times 0.05. Then we will have to take the square root of that. And we get X, which is equal to the OH minus. So from up there, has a value of 5.29 times 10 to the negative 6. All right, from OH, we can get POH. So then we do the negative log of that answer that we just got. And that gives us a POH of 5.28. So then we can finally get our pH. We do 14 minus that answer, and that is 8.72. And hooray, that seems reasonable because we knew our pH had to be a little bit above 7, but it shouldn't be anything crazy high. All right, these next couple of slides just show that whole problem reworked again. In case you want to see anything, you can pause it, look at it. You found the moles of the acid that were present. You found the moles of base that had been added. We then used stoichiometry to figure out how much of our salt had been produced. Then from there, we calculated Kb. We figured out the concentration of our salt. We plugged everything into Kb. Salt for X, which was equal to the OH minus, salt for POH, and then pH. All right, our last step is actually easy, no big deal. This is after equivalence point. So now the main thing is you have excess NaOH. So all we have to do is figure out how much excess NaOH we have, how many moles we have, what its concentration would be, find the POH, find the pH. So this is much easier than finding it at equivalence point. So we've added 52 milliliters of NaOH have been added. So you can do this one of two ways. You can figure out how many moles have been added minus how many moles were used for the neutralization to get your excess amount or excess moles, or you could figure out your excess milliliters and then use the molarity to get moles. Either way, you'll get to the same answer. Let's do the first way, the figure out how many moles were present. So if we added 0.1, if we had 52 milliliters, then we would have added 0.052 moles of NaOH. Total were added. Now we already know from my previous part that 0.05 moles of NaOH were needed for the neutralization or used. So therefore, we would have 0.002 moles of NaOH are present in excess. We also could have done that using a reaction and stoichiometry and treating the HCl as the limiting reactant. Okay, so we figured out our excess moles. Now we need to convert that into molarity. So we know my OH concentration is equal to these moles, the 0.002, and my total volume is 102 milliliters, so 0.102 liters. Okay, that gives me an OH concentration of 0.0196. So from the OH, I can find POH, and then I can find pH. I'm a little short on room, so I will need to erase some of this stuff here so that I've got a little bit of space to work with. We'll change colors. So POH would be the negative log of this concentration that we just found. That would give us 2.71. So then my pH would be 14 minus that. 11.8. 0.29. So even just adding 2 milliliters of excess base made our pH skyrocket. So this again explains why when we did our titrations and reagents, it was so hard to get that faint pink color, because a tiny bit more base greatly changes the pH.